try to have a very quick talk by Ljubica Oparnica, also here at Ghent University, talking about microlocal analysis of fractional type wave equations.
Yes, thank you, Michael, very much. So I will present results on microlocal analysis of fractional type wave equations, which is work which is done together with my friend from colleague and friend from Novi Sad from Department of Physics, and also with Ginter Hermann from Department of Mathematics at University of Vienna. So when we talk about fractional type wave equations, those are obtained by generalization of classical wave equation, and this is done within a theory of fractional calculus in order to model wave propagation in viscoelastic media or media displaying non-local effects. However, we end up with this kind of equation. So we have a second derivative in t, and then here in t we still have an operator where this parameter alpha comes from some properties of viscoelastic media. But we also have some fractional derivatives imposed by symmetrized fractional derivatives here of order beta, which could be between 0 and 1, and it gives this kind of describes non-local effects of also media. So these kind of equations, Dushan and Novi Sad school, let's say, we were looking for existence and uniqueness of such solutions with the tools of fractional Fourier transform or class transform. We obtained some numerical examples, but then we were interested in so-called wave speed of speed of propagation of wave propagation in the media, and we were interested actually in microlocal analysis, and then this is where Ginter Hermann enters in our work. So when you look at alpha to be 0, so this is a pure elastic case. Then if beta is between 0 and 1, then we have a representation of solution with this formula. And we want to see analogous of classical wave equation where wave propagation, speed propagation is given with this constant c here. For beta 0, this c is 0 and this is standing wave. And what about this case here? Now here this c could depend also on x or something. So actually that was our question. So then we discuss about wavefront set of these known things, and then we were interested in to determine wavefront set of this solution kernel. So for fractional wave equation, pure space with only beta here, we have a representation of the solution given via the fundamental solution of this equation. So it is given as an inverse Fourier transform of such a thing. So investigation showed that with appropriate cutoff, this function here is actually Hermander symbol of order 0 with rho 1 minus beta over 2 and 1 plus beta over 2. And for that, it was more than important that beta is between 0 and 1. So some mechanical effects also one can see there. So when one restricts that solution to the positive times, one first easily obtained that this set is actually upper bound. So
thank you very much. It's a very interesting talk. I think this is, if you can make conclusions, then this would be great.
Yeah, okay, or I can stop now. So nothing. There was also a few more equations that we were considering. So the point was that here we see that our that there is no propagation of singularities in this case, which was surprising for us. And the question is if we can reach some result with some other notion of wavefront set.
Okay, very good. Thank you. So we have, again, I should say that we don't have time for questions, unfortunately, but we have it's not a poster, but there is a web page about fractional derivatives that